Good morning, students. Can one of you please let me know if you can hear me and see my screen?
Yes, sir, we can.
All right, thank you. Okay, so today we will continue with the lecture we had on Monday, where we were explaining the reason why in the equivalent circuit our salient pole synchronous machines, we split our reactances into two components, which is the d-axis component and the q-axis component. And we've given the reasons why it's fundamental, the structure of the machine, that the flux distribution is different, and obviously you get a different armature reaction based on the reluctance of the path of the flux based on the rotor position. So along the pole axis, you're getting a certain reluctance, and in the interpole region, you're getting a different reluctance, and obviously then the armature reaction is different, and obviously the reactance of each of the axes are different. So that's why we are basically separating the two reactances. One is the d-axis and one is the q-axis. And also with we started basically based on this equivalent circuit, we've shown how the phasor diagram is drawn for the salient pole generator, right? So as you can see in the equivalent circuit, we still have our induced voltage and the terminal voltage E, and instead of having just one reactance XS, which is the synchronous reactance for cylindrical rotor, here we have basically two components. You have XD and XQ, and RA is representing your armature reactance, or what we call the stator reactance. Right, so when we look at the phasor diagram, it's very similar to your cylindrical rotor. It's just that we've splitted the currents into two components, and also now those two currents we combine with their reactances are giving you the drop across the two reactances, which is XD and XQ, which are in quadrature with respect to each other. So they are 90 degrees with respect to each other. So as I explained on Monday, normally you have E, your terminal voltage, you add it with I, then the drop across the resistor, and then you add the drop across the synchronous reactance normally. And here, instead of having one phasor, we have basically splitted that phasor into two components now, because we have two reactances. So it's the IDXD and the IQXQ, two components that basically comes from resolving the current I into two components, which is IQ and ID. And just to remind you, the reason why IDXD is basically perpendicular to ID, the phasor current, is because of the J operator in the reactance, which rotates the phasor by 90 degrees, right? So that makes IDXD parallel to E naught, which is basically parallel to IQ. And again, when you multiply IQ with JXQ in the equation that we've shown here, it's rotating the phasor again by 90 degrees, and obviously there IQXQ is parallel to XD, right? So that's the reason. And also explain that if we ignore the armature reactance, resistance, RA is 0, then this component falls out, and you end up with E naught being equal to E plus IDJXD plus IQJXQ, and that will be your equation for the salient pole generator. Okay. So with this simplification, we will find that the phasor diagram obviously will be modified slightly, where we will not have that component of I times RA. So from your terminal voltage, you just add the two components, which is IDXD and IQXQ, basically those two components here, and you end up with your terminal voltage, right? So you will find that in salient pole machines, um, the way that the phasor diagram is drawn basically determines the equations that you're going to use to basically analyze the machine, right? So it's very important that you have to basically be able to draw a sketch of the phasor diagram of how the machine, the phasor diagram looks like, in order to basically write your equations for the phasor diagram. Right. So if you look at this first operating point, where we're saying the salient power generator is operating at lagging power factor, which is basically your current I passing through the armature or the stator is lagging the terminal voltage by a certain angle phi. And as you can see, um, we added the two components here, which is IDXD and IQXQ, to get the um, resulting induced voltage. And you need to know this phasor, basically, that allows you to position your current IQ, right? So if you have the current I here, IQ will be along E naught, and then it will basically position ID 90-degree with respect to IQ, right? So now with the positioning of those two phases, it generates a certain angle here, which I've written here. So as you know, angle phi is your power factor angle, right? So cos of phi will be equal to the power factor. And angle delta, you're familiar with that. So that's your load angle. So that's the angle between E naught and E, right? So the induced voltage and the terminal voltage, right? So in this particular configuration of the phasor diagram, you find that the angle between IQ and I is basically the sum of delta and phi. Okay, so I've written this here: delta plus phi, and we've introduced a new angle, right? So sorry, it's phi plus delta here. That's basically giving you this angle, and the reason why we've combined those two angles is we want to find the two components of the current, right? So you need to know what is this angle here so that you can resolve the phasor I into two components. So you can see there, when I resolve the two components of I, current I, you can see that IQ will be because it's adjacent to the angle. All right, so it will be the cos of phi plus delta and times I, and ID, the opposite phasor, will be I sine of phi plus delta. Okay, so that's basic vector resolution, which I'm sure you're familiar with from your mechanics. And these two resolved phasors basically are very important, because you need those two currents to eventually determine what is E naught, as we will see, right? So once you've resolved those two currents, okay, you can see that in order to write the angle sine delta, okay, So let's look at this triangle here. So if you take sine of delta here, we're getting basically this part, okay, which is parallel to this, and they are the same size. So it's IQXQ over basically this part, which is the phase E, right? So sine delta is equal to IQXQ over E, and we can replace basically the current IQ using this equation to be equal to IXQ cos of phi plus delta, right? So that's basically expressing the angle sine delta in terms of IQN cos of phi plus delta, okay? And also you can simplify, okay? So if you send this to the numerator, it will be E sine delta being equal to this expansion, okay, of the two angles here. So we're going to expand using your trigonometric identity, cos A plus B as you've studied. So here it's phi plus delta. I've done the expansion for you. And that ends up with a few mathematical operation there, basically making sine delta the subject of formula, and then sending this part to the denominator. You end up with tan delta being equal to IQ cos of phi over E plus I XQ sine delta. Okay, so when you are analyzing salient pole machines, you will find that each of the mode of operation of the machine will have a certain phasor diagram, and also this formula for the angle delta, right, which is your load angle, will basically be depending on this phasor diagram here. Okay, so if your generator is operating in lagging power factor, right, so you can use this equation, right, to determine your angle delta and eventually determine the induced voltage. Okay, so we can eventually determine what is E naught. Okay, so we're going to look at the formula also later on, how to determine E naught. Let's move to the next phasor diagram. So we've looked at lagging power factor generator. So if we move it into leading power factor operation, obviously then we're going to flip this current, which is lagging by phi, upward. Now it's going to be leading the terminal voltage, as shown here. Okay, so that's a leading power factor salient pole generator. And what I've done is, as you can see, now your current is leading the terminal voltage by a certain angle phi, and then obviously you have resolved this current into two components. You have IQ, which is along E naught, and ID, right, which is perpendicular to IQ, right? And those two currents basically gives you the two voltage drops. That's ID XD and IQ XQ. Obviously, as I said, ID XD will be parallel to IQ, right? And IQ XQ is basically parallel to ID due to the J operator in each of them. And as you can see here from the phasor diagram, the angle between IQ, right, and I here will be now the difference between angle delta and angle phi, right, to get this small angle here, which you require to resolve the current I. Okay, so if you look at the two equations there, so ID now is equal to I sine delta minus phi, and IQ is I cos delta minus phi. Okay, so you see, when the generator changes operating point from lagging power factor to leading power factor, the phasor diagram will change and all your equations will change also. And again, I will basically derive a formula for tan of delta in terms of the current and the terminal voltage. So in the same respect, I will basically determine what is sine delta. Okay, so sine of this angle here. So obviously it's subtended by this phasor here, which is IQ xq of E, same as before. It's just that now the angle inside your cosine function is no longer phi plus delta. Now it's delta minus phi, right? So we do the expansion, and we will basically factorize sine delta, and you end up with tan delta being equal to IQ cos of phi, I times xq cos of phi divided by E minus I xq sine phi. Okay, so as you can see in the lagging power factor mode, this component is I times xq cos phi, which is the same here, right? Okay, and here we had E plus I xq sine phi, and here, as you can see, when it's operating in leading power factor, the sign has changed, right? So instead of E plus, it's E minus. Okay, so that's a difference. You will have to just take note due to the change in the angle, which instead of having phi plus delta, now it's delta minus phi. Okay, you end up with this equation. Right, so you have to be able to basically draw the phasor. As you can see, the mathematical manipulation is not difficult. So once you are able to draw the phasor diagram, you can derive those basic equation very easily, ID x and IQ, and then what is delta. It's what is tan of delta. It can easily be derived if you want. But if you are willing to memorize them, that's fine. You can basically be able, from the phasor diagram, write this equation. It's fine, because what you will be required is to be able to use this equation to determine your load angle and eventually determine what is your induced voltage, as we will look at in the examples. Right, so moving on, I'm going to move to the next mode of operation of the salient pole machine. So we're going to reverse the equivalent circuit now so that the machine is operating as a motor, right? So instead of generating a certain voltage, now we're going to apply a certain voltage to the terminal, and it will absorb certain current to basically convert now electrical energy into mechanical energy. So now the motor is absorbing certain current, and your reactance is still have two components. You will have XD and XQ and ID, IQ. And now in the motor operation, we will look at how the phasor diagram looks like. If you still remember, when the machine operates in motor mode, the position of your induced voltage, right, is different as compared to the generator, as shown here. So when you operate in motor mode, what happens is now your induced voltage is lagging the terminal voltage, all right? Whereas in generator mode, your E naught is leading the terminal voltage, right? So as you can see, if we look at this phasor diagram, this is a lagging power factor motor. So obviously now your current is lagging the terminal voltage, okay? And the current I now, obviously it will lag the terminal voltage by the angle phi, and the angle between E naught and E is your load angle delta, right? So as I said, we need to resolve this phasor, okay? And for us to resolve this phasor to get IQ and ID, we need to know what is the angle between I and E naught, right? So from this phase diagram, you can see that that small angle between E naught and I is now the difference between the angle phi and angle delta. So it will be phi minus delta, all right? And the induced voltage, right, E naught, as we've done before, it's normally the phasor I minus the two phases there, which is IDJ XD and minus the phasor IQ JXQ, right? So that's in basically vector form. And we will also write the derivation to get the two components, which is ID and IQ, right? And that's, as I said, it's I sine phi minus delta in this case, okay? And obviously, when you have phi minus delta, it will change the equation for your tan delta, as we will see here. So now we will expand cos phi minus delta here into two components, and that gives us tan delta being equal to I times xq cos of phi e minus I xq sine of phi, right? So this is the equation that you have to know for lagging power factor motor, how to determine ID, IQ, and how to get the angle delta, right? Okay, so everything is straightforward. From the phasor diagram, you can write those equations and derive it. If you want to memorize that equation, it's fine. Okay, let's move to the next configuration, which is when your motor now is operating in leading power factor mode, right? So the current now moves into leading angle with respect to the terminal voltage. So the angle difference is phi, and we keep obviously as its motor up mode, your E naught is lagging E by a certain angle delta, okay? And we will resolve the current I to two components, IQ, which is along E naught, and then ID is perpendicular with respect to IQ, right? So you can see the equation for the motor will be the terminal voltage, right, minus IDJXD plus or minus IQJXQ will give you E naught, okay? And we can write those two components, which is ID and IQ, but you have to just be careful here. The angle that's between I and E naught, right, as you can see here, is now the sum of phi and delta, okay? So the two components, I sine phi plus delta and I cos phi plus delta, now, as you can see, the two resolved components has changed due to the power factor of the motor. Okay, so those two components have their formulas has changed, And we can also determine what is sine of delta, okay, in order to get eventually tan delta. So sine of delta is basically this component, which is IQXQ over E, and you can send the E there and substitute and expand, all right? So you end up with tan delta being equal to IXQ cos of phi E plus IXQ sine of phi, right? So if we recap, so these formulas you'll be required to remember them. In the motor mode, if it's lagging power factor, you need to be able to draw the phasor diagram as shown here, right? Having your basically a lagging power factor current and be able to draw the terminal voltage and the two drops across the reactance to determine the induced voltage. And you must be able to write the two components, ID and IQ, and obviously your angle tan of delta. Okay, so again, for leading power factor, you need to be able to draw the phasor diagram and write the two components for ID and IQ and the equation for tan delta. Okay, so now as discussed in the previous lecture, ID and XD and XQ are different. As I said, it's due to the difference in the non-uniform air gap in a salient pole machine, and obviously armature reaction is different along the pole axis and the interpole area. And so typical value that you will find is that your, as I said, XQ is smaller than XD, right? And by white factor, it's normally between 0.5 to 0.8 times XD. Okay, so this is what you will encounter in typical salient pole machines. Now, if you remember, the equation for power transfer in synchronous machines was very simple when you were dealing with the cylindrical rotor machines, because you didn't have this saliency effect where XD was equal to XQ, and we basically call it XS, which is the synchronous reactance. But now, when you have this effect of saliency that affects your synchronous reactance, and obviously now you have two components, that will change the equation for the power. Okay, so this is how now your equation will look like for the power transfer in the motor and the generator. So we did introduce this concept in Machines 2, but we didn't actually write the full formula for the effect of saliency. And here we are showing why, if you can remember, we had two curves in the Machines 2 course where we were showing what is the power transfer due to the field power and what's due to the saliency power. Now, if you look at this curve that we encountered in Machines 2, you will have your normal sine curve for the field power excitation, as I said. And if you remember, we introduced this one, the saliency curve in Machines 2, and we said that when you add those two curves, what happens is the resultant power is basically shifted. The peak is shifted a little bit before 90 degrees, right? And the magnitude of the resulting power is higher than that of the cylindrical rotor machine, right? So as you can see, the amplitude is a little bit higher and it drops in terms of the angle, right? So now we are writing the full equation of that curve, which is the resulting curve. It's given by those two components. One is your field power, which is you're familiar with, E naught sine delta over XS before, and now it's XD, right? And the saliency part, right, is this component. As I explained in the previous lecture, the frequency of your saliency effect is like twice that of the cylindrical rotor, and that's why you can see now you have 2 delta there, sine 2 delta instead of sine delta, because the frequency of that sinusoidal flux in the air gap, as we showed in the previous slide, it was twice. So obviously here you'll have sine 2 delta. Okay, so this is the overall part, which is your salient part of the power. So it's E squared, right, times xd minus xq sine 2 delta divided by 2xd xq. Right? So now, when you're working out the power transfer, you have 2 components to work out, your field power and the saliency power, and add them together to get the total power transfer. Okay, so that's the resultant power that's due to both components, which is the field power and the saliency power, right? And if we look at the effect of excitation on the power that's either being generated if the motor is in generator mode, or it's absorbing if it's in motor mode. As you can see, when we vary the field excitation, obviously your value of the induced voltage will change. So we looked at different values here. So when you vary the field excitation from 0 to up to 1.5 per unit, obviously E naught is changing also from 0 to 1.5 per unit. And as you can see, initially, if you drop your field excitation to 0, okay, so if you go back to this equation here, if your field excitation or your field current is 0, what will happen is this component will basically be 0, okay? So that's your power due to the field circuit. And then you end up with only the salient power that's basically being represented by this curve here, right? So at this point, when the field current is 0, we end up with this curve, which is which gives you the maximum at power at 45 degrees. So if you remember, that was discussed in a Machines 2 course, why it is at 45 degrees. You have to just revise the notes if you've forgotten. And now if you start to increase the field current, as you can see, if you reach 1 per unit at E naught, E being equal to 1 per unit, this is how the curves looks like. Obviously, it's this shifted resultant power, which is this one here, that's being represented here. And you can also over-excite the machine by moving it to 1.5 per unit. And as you can see, that's pushing the power at maximum power close. As you keep on increasing the field current, the maximum power will increase, and it gets closer to 90 degrees, but it's not exactly at 90 degrees because of the effect of the salient power. Right, so this is the effect of changing field currents on your salient pole machine. And it's showing you that if you drop it to 0 completely, you will end up with only the salient power. And as you increase the field current to into, for example, over-excitation mode, you can see now the field power is kind of taking over the effect of the saliency. It's getting closer to that of a cylindrical rotor machine, but it's not. It never comes to 90 because you always have that salient power effect on the machine. Okay. We in terms of the notes for this section, we've covered most of what is required. I just wanted to introduce one example today so that we can just have a look at how salient pole machine can be analyzed. So the typical data that will be given to you for a salient pole machine will be obviously your rating, right? And so this, for example, this is a 1.5 MVA, and that's your line voltage, and you're given the rated voltage of the machine and the frequency. And here you've been given the XD and XQ, right? So those two reactances are given to you. And in this particular question, they are neglecting the armature resistance, okay? And they've also given you the open circuit characteristic of the machine, right? So how does the field current and the induced voltage changes when you vary your field current? Okay, so the first part, they've asked us to determine what is the induced voltage. So typical under a certain operating condition here, and they've specified rated apparent power, okay? And so basically it's operating at 1.5 MVA and 0.8 lagging, okay? So they've asked us to draw the phasor diagram in per unit and also determine the field current, IF. Okay, so for us to, you will see that in the salient pole machine, we are basically working in per unit. You will find that most of the time, okay? And so if the machine is operating at rated power and rated voltage, so if you look at, okay, so if we look at example 1, as I was explaining, if the machine is operating at rated power and voltage, so we're going to use this equation that we've derived. Yeah. As you can see, tan delta is I xq cos phi plus E I xq sine phi. So they've given us the power factor, right? So we can determine phi, right? It's 0.8 power factor lagging. So obviously we can determine those two components. What is sine phi and what is cos phi and sine phi? One is 0.8, one is 0.6. All right. And they've given us xq, which is 0.8 per unit. And what is important here, as I was noting, is if it's operating at rated load, so your terminal voltage will be per unit, and your current is also 1 per unit because it's operating at full load. And obviously you can take the current to be 1 per unit, okay? So if you substitute in this equation that we've derived earlier, you can determine this value of tan delta, which is 0.4324, and obviously you can determine the value of delta, okay? So once you've determined the value of delta, okay, you can also now basically write the equation for E naught, okay? So if we look at the phasor diagram, 1 second. Okay, so if you look at the phasor diagram, as you can see, if you want to determine this this value E naught here, okay, so that's the induced voltage. So you can see that if you resolve this phasor E here, terminal voltage, so the component that will be acting along the induced voltage will be E cos theta. Okay, so this phasor will be from here up to this point here, right? And the remaining part will be from here, from this point to here, it will be ID xt. Okay, so if we know what is E cos delta, by adding this part, which is ID xt here, the second part here, we can determine E naught. Okay, so this is what I've done here. So I've said that I've determined delta and I've determined the two currents. Okay, so first I've substituted from this equation here, which is E naught is equal to E cos theta plus I dxt, right? You need to now basically expand this one, this component ID, to be equal to I times sine phi plus delta, okay? So we're going to use those two angles that we've determined from the previous steps to solve for E naught, right? So E cos delta is straightforward. So we know what is the magnitude of the phasor. It's 1 per unit. So cos delta, we just substitute there. And for I, we basically have 1 per unit. Xt is given. So that's 1.2. And here, importantly, we need to have phi plus delta. Okay, so that's phi plus delta. So you substitute and you can get the magnitude of the induced voltage. And also, now remember that E naught is the angle. So if you write it in vector form, you need to add the angle, and E naught will obviously lead the terminal voltage by the angle delta. So that's positive here. And this is how you get the induced voltage per phase in per unit for this salient pole machine. Okay, so this kind of analysis now, as you can see, it will vary depending on the type of operation or the operating point of the machine, whether it's operating in lagging power factor or leading power factor. So those equations will basically change, specifically the one that's in between the bracket there. So whether it's phi plus delta or phi minus delta minus phi, that will depend on the power factor of the machine. Okay, so going further, as you can see from the value that I've obtained here for E naught, I've worked out what is the line-to-line voltage. So you multiply by √3 to get the line-to-line voltage. And then remember, they asked us to determine what is the field current for this particular operating point. So as you can see here, I have used what we call the modified air gap line. Okay, so that's what we looked at in the previous course. When your machine is operating under load and you want to determine the field current, we use what we call the modified air gap line. So that one, you take the rated voltage, right, and at which this is your corresponding field current, and you take the ratio and you multiply by the voltage to get the field current for the new operating voltage, right? So that's using the modified air gap line to determine the field current for this particular operating point, which is at E naught being equal to 45.6 sorry, it's 44,508 volts. All right, so once you've basically determined this voltage, I've drawn the phasor diagram for this particular machine. As you can see now, you have all these values to determine your ID, IQ. So this phasor diagram is in per unit, and I've determined what is ID, XD, IQ, XQ. So it requires quite a bit of calculations there. So what I'd advise you to do is to practice this question by yourself first. So just take pen and paper and try and solve this example yourself, okay? And then determine all these values by yourself and draw the phasor diagram by yourself, and then you can compare and see whether you're getting the same values as I've basically shown in the solution here. Right, so in terms of studying for your machines course, you have to, whether it's a tutorial question or an example, you have to always don't just look at the solution and try to study, because you will find that eventually you lack understanding. You have to take pen and paper and solve the question yourself and then compare. That's the way you're going to basically build your confidence in terms of understanding the concept of the phasor diagram and what equation you require, and that basically prepares you for your assessment. So until we're going to meet in the next lecture. So try and practice the question, and then I will continue in the next lecture, which will start after this period. All right.